In the darkness beyond Neptune's orbit, two objects drift through space with velocities that betray their alien origins. They move too fast for captivity by our sun's gravity, their trajectories carved by forces that began in stellar nurseries dozens of light years away. When the universe was hundreds of millions of years younger, and the galaxy's spiral arms held different configurations of dust and gas. One tumbles end over end, a reddish shard perhaps 400 meters long, its surface weathered by cosmic rays and micrometeorite impacts accumulated over millions of years in the interstellar medium. The slow bombardment of high-energy particles has gradually altered its surface chemistry, converting simple organic molecules into complex polymers that absorb blue light and reflect the deeper wavelengths, painting it the color of rust or dried blood. The other trails a gossamer tail of sublimating ice, glowing faintly in the distant sunlight like a celestial brushstroke painted across the void. As solar radiation heats its surface, buried volatile compounds, water ice, carbon monoxide, nitrogen transition directly from solid to gas, carrying with them microscopic dust grains that catch and scatter photons in a process unchanged since comets first formed in the outer regions of stellar disks. The tail points away from the sun, shaped by radiation pressure and the solar wind into a structure that extends for millions of kilometers, visible only because space telescopes can detect the faint fluorescence of excited molecules against the cosmic background. Both are visitors from the galactic deep, messengers from star systems that formed when our own solar system was still a swirling disk of dust and possibility. Their journey through interstellar space has exposed them to conditions unlike anything experienced by objects that remained gravitationally bound to their parent stars. The interstellar medium, though nearly empty by terrestrial standards, contains enough hydrogen atoms, helium nuclei, and dust particles to gradually erode surfaces and alter chemical compositions over geological timescales. Magnetic fields threading through the galaxy accelerate charged particles to energies that can penetrate deep into solid matter, creating new isotopes and breaking molecular bonds in a slow process of cosmic weathering. The first carries the designation Oumuamua, named for the Hawaiian word meaning scout or messenger from afar arriving first. The name itself whispers of humanity's ancient relationship with the sky, chosen by astronomers who understood they were witnessing something unprecedented in the recorded history of our species. For thousands of years, humans have watched comets appear and disappear, tracking their predictable returns, weaving them into mythology and calendar keeping. But Oumuamua represents something fundamentally different, a visitor that belongs to no solar orbit, a fragment of deep space that happened to intersect our gravitational neighborhood for a brief moment before continuing its billion-year journey across the galaxy. The second bears the more technical label 2I Borisov, later redesignated as 3I Atlas, after more careful orbital analysis revealed subtle perturbations in its path that required additional observations to resolve. The renaming reflects the challenge of tracking objects that move against the stellar background at unprecedented speeds, requiring new algorithms and observational strategies developed specifically for interstellar visitors. Their names reflect humanity's growing awareness that we inhabit not an isolated system, but a way station in the galaxy's vast migration of matter, a temporary harbour for objects whose journeys began before Earth's continents took their current shapes, before complex life emerged from the primordial oceans. These objects share a fundamental strangeness that sets them apart from every asteroid and comet catalogued in our solar system's family portrait. They move through space on hyperbolic orbits, open curves that will carry them back into interstellar darkness after their brief passage through our neighborhood. Mathematical analysis of their trajectories reveals orbital eccentricities greater than 1, meaning their paths through space describe not ellipses but hyperbole curves that approach but never close upon themselves. Their velocities exceed the sun's escape speed by margins that cannot be explained by gravitational perturbations from the known planets, marking them as permanent exiles from whatever stellar systems gave them birth. The physics of their motion speaks to violent histories. Objects achieve interstellar velocities only through catastrophic gravitational encounters, close approaches to massive planets during the chaotic early epochs of stellar system formation, or tidal disruption events when binary stars pass near developing planetary systems. Computer simulations suggest that every star system ejects vast quantities of solid material during its formation phase, launching asteroid-sized objects into interstellar space at velocities ranging from a few kilometers per second to tens of kilometers per second. The galaxy thus becomes filled with debris from countless episodes of planetary formation, a vast ocean of wandering fragments that occasionally intersect the gravitational sphere of influence of other stellar systems. Yet their differences hint at the diversity hidden in the cosmic deep, the vast population of wanderers that drift unseen through the galaxy's spiral arms. One shows no visible activity, its surface darkened by eons of radiation exposure, a process that gradually converts organic compounds into complex carbon chains that absorb sunlight across the visible spectrum. The darkening occurs because cosmic rays break apart methane, ammonia, and other simple molecules, creating free radicals that recombine into larger structures resembling asphalt or charcoal. This process, known as space weathering, operates continuously on any surface exposed to the interstellar radiation field, gradually reducing reflectivity and reddening color over timescales measured in millions of years. Astronomers measure its color as unusually red, similar to objects in the outer reaches of our own solar system that have been cooked by cosmic radiation for billions of years. The Kuiper Belt objects and long-period comets show similar spectral signatures, suggesting common processes of surface alteration that operate wherever ice and organic compounds meet high-energy radiation. Yet subtle differences in the absorption features hint at compositional variations, different ratios of carbon to oxygen, varying abundances of nitrogen-bearing compounds, trace elements that reflect the unique chemistry of the stellar nursery where formation occurred. The other behaves like the comets we know, shedding material as it approaches the sun's warmth, its coma and tail revealing familiar molecules, water vapor, carbon monoxide, dust grains that catch and scatter light in patterns that speak of ice sublimating into vacuum. Spectroscopic observations detect the characteristic emission lines of hydroxyl radicals, the photodissociation products of water molecules broken apart by solar ultraviolet radiation. The coma expands symmetrically around the nucleus, creating a roughly spherical cloud of gas and dust that extends for hundreds of thousands of kilometers, visible in telescopic images as a fuzzy patch that obscures the central object. Both challenge our understanding of what wanders between the stars, and both arrived at a moment when human technology could finally recognize them for what they are. Only in the past few decades have our telescopes become sensitive enough to detect such small, dark objects racing through the outer solar system at unprecedented speeds. The challenge lies not merely in their faintness, though they reflect only a tiny fraction of the sunlight that illuminates them, but in their rapid motion against the stellar background. Traditional asteroid surveys search for objects that move slowly across the sky, following predictable paths that can be extrapolated from a few nights of observation. interstellar visitors move too quickly for such leisurely analysis, requiring immediate follow-up observations before they fade beyond the reach of ground-based telescopes. The Panoramic Survey Telescope and Rapid Response System, known as PAN-STARRS, and the Catalina Sky Survey represent humanity's first systematic attempt to monitor the sky for exactly these kinds of visitors. Their CCD cameras sweep the heavens night after night, comparing new images with archived observations, searching for points of light that move too fast and in the wrong directions. The automated detection algorithms flag objects whose motion vectors indicate hyperbolic orbits, triggering alerts that mobilize observational resources around the world. This represents a new kind of astronomy time domain surveys that monitor the entire visible sky for transient phenomena, capturing events that would have been missed entirely by previous generations of astronomers. The universe has been sending us these gifts for billions of years, only now we have learned to see them. Statistical models derived from the detection rates of Oumuamua and subsequent visitors suggest that several interstellar objects pass through our solar system every year, most too small or too distant to detect with current instruments. The calculations paint a picture of constant traffic through the outer solar system, a steady stream of wandering fragments that approach from random directions, follow hyperbolic trajectories round the Sun, and disappear back into the cosmic deep without leaving any trace of their passage, except for the gravitational perturbations they impart to dust particles and the occasional asteroid. We live in a cosmic shooting gallery, bombarded constantly by debris from stellar formation processes that occurred when the galaxy was young. Every cubic parsec of interstellar space likely contains thousands of these wandering fragments, the scattered remains of planetary systems that formed, evolved, and were torn apart by the gravitational dance of binary stars or the violent death throes of their parent suns. The density of interstellar objects probably varies with location in the galaxy, higher near star-forming regions where planetary systems are currently ejecting material, lower in the voids between spiral arms, where only the oldest wanderers survive their million-year journeys through near-empty space. The recognition of this hidden population transforms our understanding of galactic ecology. Stars do not evolve in isolation but participate in a vast exchange of matter that connects stellar systems across hundreds of light-years. Gravitational interactions during the early epochs of planetary system formation launch solid material into interstellar space at velocities sufficient to reach neighboring star systems within a few million years. This process, known as lithopanspermia, could theoretically transport not only minerals and organic compounds, but also microbial life between worlds, seeding the galaxy with the chemical precursors of biology, or even living organisms capable of surviving the harsh conditions of interstellar space. Computer simulations of stellar system formation reveal the violent dynamics that create these wandering populations. During the first few million years after a protoplanetary disk begins to condense into solid bodies, gravitational interactions between embryonic planets scatter vast quantities of smaller objects onto trajectories that carry them beyond the gravitational reach of their parent star. The process resembles a cosmic pinball machine, with developing planets acting as gravitational slingshots that accelerate debris to escape velocity. Objects that approach too closely to massive worlds receive gravitational kicks that can double or triple their orbital velocities, transforming stable members of a planetary system into permanent exiles. The same mechanisms operate in reverse when these wanderers encounter other stellar systems during their galactic wanderings. Occasionally, an interstellar object passes close enough to a massive planet to lose energy through gravitational interaction, trading velocity for a more tightly bound orbit that transforms the visitor into a permanent resident. Jupiter's gravitational influence dominates such capture processes in our solar system, though the probability remains extremely low. Most interstellar visitors pass through the outer solar system without coming close enough to any planet to significantly alter their trajectories, continuing their journeys with only minor perturbations from the Sun's gravity well. Theoretical studies suggest that captured interstellar objects might be hiding in plain sight among the irregular satellites of the giant planets, or in co-orbital resonances with Jupiter and Saturn. These objects would be indistinguishable from native solar system bodies after billions of years of orbital evolution. Their interstellar origins erased by the gradual effects of planetary perturbations and tidal forces. Some of the Trojan asteroids that share Jupiter's orbit might be ancient interstellar captures, their unusual compositions and orbital properties preserving subtle clues about their foreign origins. The outer satellites of the giant planets, with their distant, highly inclined orbits, represent another possible hiding place for objects that entered our solar system from interstellar space during its early history. Yet the vast majority of interstellar visitors remain unbound to our gravitational system, following open trajectories that carry them back into the galactic deep after their brief encounter with solar warmth. Like planetary archaeologists examining ancient artifacts, we measure their light and calculate their paths, extracting stories written in spectral lines and orbital mechanics. Each visitor carries chemical signatures from distant worlds, frozen samples of stellar evolution, compressed narratives of galactic history encoded in the ratios of isotopes, and the presence of trace elements that formed in the nuclear furnaces of alien suns. Spectroscopic analysis reveals the fingerprints of familiar molecules: water ice, carbon monoxide, nitrogen, silicate minerals, the basic building blocks of rocky worlds and icy bodies that apparently form around other stars through processes similar to those that shaped our own solar system. These measurements provide our first direct sampling of matter from beyond our solar system, allowing us to test theories about planet formation and stellar evolution against actual physical evidence, rather than relying entirely on theoretical models and observations of distant protoplanetary disks. The chemical composition of interstellar visitors also constrains models of galactic chemical evolution. Different stellar populations produce different ratios of heavy elements through nucleosynthesis, creating gradients in metallicity that vary with distance from the galactic center and with stellar age. Interstellar objects preserve records of the chemical conditions that existed in their birth environments, potentially allowing astronomers to trace their origins back to specific regions of the galaxy or even specific types of stellar systems. Isotopic ratios of carbon, nitrogen, and oxygen could reveal whether an object formed in the disk of a metal-rich star or in the outer regions of a metal-poor system, while the presence of unusual isotopes might indicate formation near a supernova or in the outflow from an evolved giant star. They drift past our cameras and spectrographs in a matter of months, their brief appearances measured in observing sessions and telescope time allocation committees. Ground-based observatories coordinate worldwide campaigns to track these objects as they race toward perihelion and then fade into the cosmic background, their angular velocities often exceeding the tracking limits of large telescopes designed to follow slowly moving targets. Space-based telescopes like Hubble and Spitzer contribute their unique capabilities, imaging the visitors in wavelengths invisible to human eyes, searching for clues about their composition and internal structure that cannot be obtained from ground-based observations. Each observation becomes precious, irreplaceable data that will never be duplicated, for these objects follow one-way trajectories that carry them beyond the reach of our most powerful instruments. The observational campaigns require careful coordination between multiple facilities, with astronomers racing against time to gather as much information as possible before the visitors disappear forever. Priority targets receive round-the-clock monitoring, with telescopes in different hemispheres handing off observations as Earth's rotation carries each facility out of view. The data streams from these campaigns photometric measurements, spectroscopic observations, astrometric positions represent humanity's only direct encounter with matter from other stellar systems. The urgency of these observations has revolutionized certain aspects of astronomical practice. Traditional scheduling processes, with their months-long proposal review cycles, cannot accommodate targets that remain visible for only a few weeks. Instead, observatories have developed rapid response capabilities that allow high-priority observations to be scheduled within hours of target identification. This new mode of operation bridges the gap between planetary science and stellar astronomy, requiring instruments designed for solar system observations to be quickly reconfigured for studies of interstellar visitors that behave unlike any previously catalogued objects. Then they disappear forever into the darkness from which they came, their brief interaction with our star's gravity well completed, their orbital energy unchanged by the encounter, except for the tiny momentum transfer associated with radiation pressure and the emission of thermal photons. They continue their journeys across the galaxy at speeds measured in kilometers per second, carrying with them whatever secrets they acquired during their formation in alien stellar nurseries billions of years ago. In 1,000,000 years, they will be light years away, still tumbling through the void, still preserving their cargo of ancient ice and primordial rock, still bearing witness to the processes that shaped worlds we will never visit. The vastness of their future trajectories dwarfs human comprehension, distances so large that light itself, travelling at the ultimate speed limit of the universe, requires years to cross the gaps between their current positions and their eventual destinations. Yet these objects maintain their structural integrity across such spans of time and space, their surfaces slowly evolving under the constant bombardment of cosmic radiation, while their interiors remain frozen in the conditions that existed when they first condensed from the cooling debris of stellar formation. The physics of their survival speaks to the remarkable stability of solid matter in the near vacuum of interstellar space. Unlike objects orbiting close to active stars, interstellar wanderers experience minimal heating and virtually no atmospheric drag or tidal forces that could disrupt their structure. The primary agents of change operate on geological timescales. Cosmic ray bombardment gradually alters surface chemistry. Micrometeorite impacts create new crater fields and expose fresh material, and the slow sublimation of volatile compounds reshapes topography over millions of years. These processes proceed so slowly that objects launched from stellar systems during the galaxy's youth could still preserve recognizable traces of their original composition today. Temperature measurements of interstellar objects reveal the profound cold that characterizes their environment. Far from any stellar heat source, their surfaces equilibrate with the cosmic microwave background radiation at temperatures near 3 degrees above absolute zero. At such temperatures, most chemical reactions proceed infinitely slowly, and even quantum tunneling effects that normally facilitate molecular transformations become negligible. Water ice becomes harder than steel, nitrogen freezes solid, and organic compounds enter a state of chemical suspended animation that could preserve complex molecules for billions of years. This natural refrigeration creates time capsules that sample the chemical conditions existing in stellar nurseries when the galaxy was young. The recognition that these objects exist transforms our understanding of the solar system from an isolated island to a harbour in the galactic ocean. We are not alone in our corner of the Milky Way, but connected through the constant traffic of interstellar matter to every star system in our neighbourhood. The same gravitational processes that ejected these visitors from their birth systems continue to operate today, launching new wanderers into the cosmic deep while capturing others in temporary gravitational embraces. Our own solar system contributes to this galactic diaspora, ejecting comets from the Oort cloud through interactions with passing stars and scattering asteroid fragments through close encounters with Jupiter and the other giant planets. Statistical analyses suggest that our solar system has probably launched millions of objects into interstellar space during its 4 billion-year history. The most massive ejection events likely occurred during the late heavy bombardment, when migrating giant planets gravitationally scattered vast populations of asteroids and comets throughout the solar system. Some fraction of this debris received sufficient energy to escape the Sun's gravitational influence entirely, carrying samples of Earth's neighbourhood into the broader galaxy. These objects now wander between the stars alongside visitors from thousands of other stellar systems, participants in a slow but constant exchange of solid material that connects star formation regions across hundreds of light years. The isotopic signatures preserved in meteorites provide evidence for this ancient trafficking of matter between stellar systems. Certain meteorites contain mineral grains that predate the formation of our solar system, their isotopic compositions matching the predicted outputs of specific types of stellar nuclear synthesis. These pre-solar grains survived the violent processes that destroyed and reformed most of the solid material in the early solar nebula, preserving direct samples of matter that condensed in the atmospheres of ancient red giant stars or in the expanding shock waves of supernovae. Their presence demonstrates that interstellar space contains a vast reservoir of solid material launched from countless stellar systems during their formation and evolution phases. Similar processes likely operate throughout the galaxy, creating vast populations of wandering objects that carry chemical information between star systems. The metallicity gradients observed in stellar populations suggest that this mixing process has operated throughout galactic history, gradually homogenizing the chemical composition of the interstellar medium while preserving local variations that reflect recent episodes of star formation and stellar death. Interstellar visitors represent mobile agents in this chemical evolution, transporting heavy elements synthesized in the nuclear cores of massive stars to regions of the galaxy where new generations of planets can incorporate these materials into their formation processes. Yet the detection of only 2 confirmed interstellar visitors in human history highlights the challenge of studying this population. The objects remain invisible until they pass close enough to the Sun for terrestrial telescopes to detect their reflected light, and even then they appear as point sources indistinguishable from asteroids except for their unusual orbital characteristics. Their small sizes and dark surfaces make them difficult targets for spectroscopic analysis, requiring the largest ground-based telescopes operating at their sensitivity limits to obtain even basic compositional information. Most interstellar objects probably pass through the outer solar system undetected, their brief appearance against the stellar background falling between the observational cadence of automated sky surveys. The development of more sensitive detection systems promises to revolutionize our understanding of the interstellar object population. The upcoming Legacy Survey of Space and Time, conducted by the Vera C. Rubin Observatory, will monitor the entire southern sky every few nights with unprecedented depth and temporal resolution. Computer models predict that this survey could detect dozens of interstellar visitors each year, providing the statistical sample sizes necessary to characterize the population as a whole, rather than relying on the unique properties of individual objects. Space-based infrared telescopes could detect the thermal emission from interstellar objects too dark to observe in visible light, extending the detection range to smaller and more distant targets. Future interstellar visitors might even become targets for robotic space missions, though the technical challenges remain formidable. The high velocities of hyperbolic objects require massive energy expenditures to achieve rendezvous trajectories, while their unpredictable arrival times make it difficult to prepare missions in advance. Conceptual studies have explored the possibility of high-velocity flyby missions that could return close-up images and compositional measurements without attempting to match orbital velocities. Such missions would require new propulsion technologies and spacecraft designs optimized for brief encounters at relative speeds measured in tens of kilometers per second. The brief passage of each interstellar visitor through our detection zone represents a unique opportunity to sample matter from distant stellar systems without the expense and complexity of interstellar travel. These objects serve as natural space probes, carrying physical samples across distances that dwarf the scale of human space exploration and delivering them to convenient locations within our own solar system. Their chemical and isotopic compositions provide ground truth for theories about planet formation, stellar nucleosynthesis, and galactic chemical evolution that would otherwise remain forever beyond the reach of direct experimental verification. This realization brings with it a kind of cosmic loneliness. We are part of something much larger than ourselves, yet forever separated by distances that dwarf human comprehension. The interstellar visitors connect us to the broader galaxy, while simultaneously emphasizing our isolation. They carry news from stellar systems that will never appear as more than points of light in our most powerful telescopes, samples from worlds whose surfaces we will never map, chemical signatures from processes that occurred when the universe was young. Their silent passage through our neighborhood serves as a reminder that we inhabit a small oasis of warmth and complexity in an ocean of dark, cold emptiness populated by wandering fragments of ancient worlds. The first recognition came quietly, without fanfare, embedded in the routine data streams of an automated sky survey operating from a mountaintop in Hawaii. On October 19, 2017, the Panoramic Survey Telescope and Rapid Response System detected a faint point of light moving against the stellar background at an angular velocity that immediately flagged it as unusual. The object appeared unremarkable in initial observations, a dim speck reflecting sunlight like thousands of other small bodies that populate the outer solar system. Yet its trajectory told a different story, one that would force astronomers to confront the reality that our solar system receives regular visits from fragments of alien worlds. Robert Varick, the astronomer who first noticed the anomalous motion, recalls the moment of realization when preliminary orbital calculations revealed an eccentricity greater than 1. Such values indicate hyperbolic trajectories, open curves that approach the Sun from interstellar space and then depart forever, rather than the closed ellipses that characterize objects gravitationally bound to our stellar system. The mathematics contained an unmistakable signature. This object originated beyond the gravitational influence of the Sun, arriving from the direction of the constellation Lyra after a journey that likely lasted millions of years through the cosmic void. The discovery triggered a worldwide observational campaign as astronomers raced to characterize the visitor before it faded beyond the reach of ground-based telescopes. Major observatories around the globe redirected their instruments toward the rapidly moving target, coordinating observations across multiple wavelengths and time zones to maximize the scientific return from this unprecedented opportunity. The urgency stemmed from the object's trajectory. It was already past its closest approach to the Sun and accelerating back toward interstellar space, its apparent brightness decreasing daily as it receded into the outer solar system. Initial spectroscopic observations revealed a surface composition that defied easy categorization. The object reflected light with a distinctly reddish color, similar to some asteroids in the outer solar system that have been darkened by eons of cosmic radiation. Yet it showed no signs of cometary activity, no coma of sublimating ice, no tail streaming away from the solar wind. Its spectrum lacked the characteristic absorption features of water ice or hydrated minerals that astronomers expected to find on an object that had survived a multi-million-year journey through the interstellar medium. Instead, the reflected light suggested a surface covered in organic compounds that had been gradually polymerized by high-energy radiation into complex carbon chains. The object's rotation presented another puzzle. Photometric observations revealed brightness variations that repeated every 34 hours, indicating that the visitor tumbled end over end as it traveled through space. The amplitude of these variations, the difference between maximum and minimum brightness, suggested an extremely elongated shape, perhaps 10 times longer than it was wide. Computer models attempting to match the observed light curve required aspect ratios that pushed the boundaries of structural stability for solid objects, leading to speculation about whether the visitor might be a fragment of a larger body that had been tidally disrupted during a close encounter with a massive planet or stellar companion. The International Astronomical Union faced the unprecedented challenge of naming humanity's first confirmed interstellar visitor. Traditional nomenclature for asteroids and comets assumes objects that belong to our solar system, following predictable orbits that can be catalogued and referenced indefinitely. But this object would disappear forever after its brief passage, never to return to the inner solar system. The naming committee ultimately chose Oumuamua, a Hawaiian word meaning scout, or messenger from afar arriving first, acknowledging both the observatory that discovered it and the profound significance of its interstellar origin. As observational data accumulated, the object's unusual properties deepened rather than resolved the mysteries surrounding its nature and origin. High-resolution imaging attempts with the Hubble Space Telescope failed to reveal any extended structure or surface features, confirming that the visitor was indeed very small, probably no more than a few hundred meters in its longest dimension. Its lack of detectable cometary activity puzzled astronomers who expected any icy object to show signs of sublimation when heated by solar radiation, especially one that had spent millions of years in the near absolute zero environment of interstellar space. Thermal infrared observations provided additional constraints on the object's properties. The visitor absorbed solar energy during its passage through the inner solar system and re-radiated that energy at longer wavelengths characteristic of its surface temperature. The balance between absorbed and emitted radiation allowed astronomers to estimate the object's size and albedo, the fraction of incident sunlight that it reflected rather than absorbed. These measurements confirmed that Oumuamua was both small and dark, reflecting only about 10% of the sunlight that illuminated its surface, similar to the darkest asteroids in our own solar system. The trajectory analysis revealed subtle but significant deviations from a purely gravitational orbit. As Oumuamua receded from the Sun, it accelerated slightly faster than Newton's laws predicted, as if some additional force was acting to increase its velocity. The magnitude of this non-gravitational acceleration was tiny, about 1 part in 10,000 of the Sun's gravitational pull at the object's position, but it was statistically significant and persistent across multiple observations. Similar accelerations characterize active comets, where the rocket effect of sublimating ice provides a small but measurable thrust that modifies orbital trajectories over time. Yet Oumuamua showed no visible signs of the gas and dust emission that typically accompanies cometary outgassing. Sensitive observations with ground-based telescopes and the Spitzer Space Telescope searched for the characteristic signatures of water vapor, carbon monoxide, and dust particles that should have been detectable if the visitor was shedding material at rates sufficient to explain its anomalous acceleration. The non-detections placed upper limits on outgassing rates that were orders of magnitude lower than those observed from active comets at similar distances from the Sun. This contradiction between the object's cometary-like acceleration and its asteroid-like appearance sparked intense debate about the visitor's true nature. Some astronomers proposed that Oumuamua was predominantly rocky, like an asteroid, but contained small deposits of volatile material in subsurface pockets that could sublime without creating a detectable coma. Others suggested that the object might be composed of unusual materials, perhaps nitrogen ice that would sublime at lower temperatures than water, or organic compounds that could outgaze without producing the spectroscopic signatures typically associated with cometary activity. The mystery deepened when theoretical studies examined the probability of detecting such an object. Statistical models based on stellar formation rates and planetary system evolution predicted that interstellar visitors should be relatively rare, with only a few objects passing through the inner solar system each century. The discovery of Oumuamua so soon after systematic sky surveys achieved the sensitivity necessary to detect such objects seemed remarkably fortunate, or perhaps indicative of a much larger population of interstellar wanderers than theoretical models predicted. As Oumuamua faded beyond the detection limits of even the most powerful telescopes, it left behind more questions than answers. Its brief passage through our solar system had confirmed that interstellar objects exist and occasionally visit our neighborhood, but its unusual properties defied easy categorization within the traditional framework of asteroid and comet science. The visitor challenged assumptions about the nature of small bodies in interstellar space, the efficiency of various detection methods, and the frequency with which alien material intersects our gravitational domain. The mystery of Oumuamua's strange accelerations lingered in the scientific literature like an unsolved riddle, spawning dozens of theoretical papers that attempted to explain how an apparently inert object could exhibit the dynamical behavior typically associated with active comets. The non-gravitational forces acting on the visitor were real and measurable, detected independently by multiple observational teams using different telescopes and analysis techniques. Yet the physical mechanism responsible for these forces remained elusive, hidden beneath the object's dark, unreflective surface, and obscured by the vast distance that separated it from Earth-based instruments. Traditional explanations for non-gravitational accelerations in the solar system invoke the rocket effect of sublimating volatiles water ice, carbon monoxide, nitrogen, and other compounds that transition directly from solid to gas when heated by solar radiation. The escaping gas streams carry momentum away from the object's surface, creating a small but persistent thrust that can significantly alter orbital trajectories over time. Comets routinely exhibit such behavior, their spectacular tails serving as visible evidence of the mass loss that drives their non-gravitational motions. Yet Oumuamua showed no signs of the gas and dust emission that should accompany significant outgassing. creating a paradox that challenged conventional understanding of small body physics. Some astronomers propose that the visitor might be shedding material composed of molecules too small or too dispersed to detect with existing observational techniques. Hydrogen gas, for instance, would be virtually invisible to most spectroscopic surveys, but could still provide sufficient thrust to explain the observed accelerations if produced in large enough quantities. The photodissociation of water ice could generate hydrogen through a multi-step process. Solar ultraviolet radiation breaks apart water molecules into hydrogen and oxygen atoms, and the light hydrogen atoms escape into space, while the heavier oxygen remains bound to the surface. This mechanism could operate even when traditional cometary activity remains below detection thresholds. Alternative theories explored more exotic possibilities. Perhaps Oumuamua was not a conventional rocky or icy body, but rather a fragment of unusual composition that could outgaze without producing detectable emissions. Nitrogen ice, for example, sublimates at lower temperatures than water and produces gas that lacks strong spectroscopic features in the wavelength ranges, typically monitored by astronomical surveys. If the visitor originated in a stellar system with different chemical abundances than our own, it might be composed of materials that behave in unexpected ways when exposed to solar heating. The most speculative explanations ventured into uncharted theoretical territory. Some researchers suggested that Oumuamua might be an artificial object, a piece of alien technology that happened to pass through our solar system during its multi-million-year journey between the stars. The object's unusual shape, its lack of detectable outgassing, and its anomalous acceleration could all be explained if it were constructed rather than naturally formed. While such scenarios remained highly speculative and unsupported by direct evidence, they highlighted the degree to which the visitor's properties challenged conventional explanations. Radiation pressure offered another potential mechanism for the observed accelerations. Sunlight carries momentum as well as energy, and when photons are absorbed or reflected by a solid surface, they transfer that momentum to the object. For small bodies with low densities and high surface area to mass ratios, radiation pressure can provide measurable accelerations that modify orbital trajectories. Computer models suggested that Oumuamua might have an extremely low density, perhaps comparable to aerogel or another highly porous material that would make it susceptible to radiation pressure effects large enough to explain its non-gravitational motion. The thermal recoil effect, known as the Yarkovsky effect, could also contribute to the observed accelerations. Objects in space absorb solar energy during their daytime periods and re-radiate that energy as thermal infrared photons during their nighttime periods. If the object rotates slowly enough, the peak thermal emission occurs when the warmest surface faces away from the sun, creating a net thrust in the direction of orbital motion. For Oumuamua, which rotated every 7.34 hours and had an elongated shape that would create strong thermal gradients across its surface. The Yarkovsky effect could potentially produce accelerations of the right magnitude to match observations. Yet each proposed explanation carried its own set of assumptions and limitations. The hydrogen outgassing model required that Oumuamua be composed almost entirely of water ice, despite spectroscopic observations that suggested a rocky or carbonaceous composition. The nitrogen ice hypothesis demanded formation conditions unlike those found in our own solar system, implying that the visitor originated in a stellar environment with fundamentally different chemistry. The artificial object scenario, while intriguing, remained scientifically unprovable, given the available observational data and the vast distances involved. The radiation pressure explanations required the object to have structural properties that pushed the boundaries of physical plausibility, for radiation pressure to account for the observed accelerations. Oumuamua would need to be extremely lightweight, perhaps less dense than cork or balsa wood, while maintaining structural integrity sufficient to survive millions of years in interstellar space and the thermal stresses associated with its close passage by the Sun. Such characteristics seemed inconsistent with the dark, apparently solid surface revealed by photometric observations. As observational opportunities dwindled and Oumuamua faded into the cosmic background, astronomers were forced to accept that many fundamental questions about the visitor would remain permanently unanswered. The object's true composition, internal structure, and formation history would forever remain matters of speculation rather than empirical determination. Its brief passage through our detection zone had provided tantalizing glimpses of its properties, but insufficient data to construct a complete physical model that could explain all of its unusual characteristics. The scientific legacy of Oumuamua extends beyond the specific puzzles it presented to the broader recognition that interstellar objects represent a new class of targets for observational astronomy. The visitor demonstrated that space contains populations of small bodies with properties that may differ significantly from those of objects that have remained gravitationally bound to stellar systems throughout their histories. The harsh conditions of interstellar space, extreme cold, persistent radiation, and isolation from stellar heat sources could produce surface modifications and internal structures unlike anything found among familiar asteroids and comets. Future detections of similar objects would be necessary to determine whether Oumuamua represented a typical example of interstellar wanderers or an unusual outlier whose properties reflected unique formation conditions or evolutionary processes. The visitor's anomalous characteristics might be common features of objects that have survived multi-million-year journeys through the cosmic void, or they might result from rare circumstances that would not be repeated in subsequent discoveries. Only through the statistical analysis of multiple interstellar visitors could astronomers hope to distinguish between universal properties of the population and idiosyncratic features of individual objects. The technological and observational challenges revealed by Oumuamua's discovery also highlighted the need for new approaches to studying transient astronomical phenomena. Traditional observational strategies, designed for objects that remain visible for months or years,